So what do we mean by internal resistance? So if we think about a typical power supply, so a battery or a power pack, inside the battery there are electrodes made of metal, there's chemicals. Inside a power pack, then there's going to be wires and coils and transformers. So the current has to flow through the power supply. So as the current flows around the circuit, it's got to pass through the power supply. So all this obstacle to the flow of current we call internal resistance. And it's caused by the same reasons that we get resistance in wires, because of collisions between the delocalized electrons and the vibrating atoms in metal. So we refer to this as the internal resistance. We give it the symbol R, but we normally use a little r to distinguish it from the circuit resistance, which is capital R. So if we have current flowing through an internal resistance, then we're going to get some voltage associated with that. So some voltage, some energy is used up, and this is called the lost volts, and we could calculate this by I times R. So in the same way that we have voltage as current times resistance, so the current is the same all the way around the circuit, and the resistance we're talking about inside the battery is the internal resistance. So we have something called lost volts, more on that later. So if we have an EMF, that is the maximum theoretical voltage that a power supply can deliver, so whether the battery or the power pack. And we cannot measure this directly. But the actual voltage available is going to be slightly less than this. This is referred to as the terminal PD, which is I times big R, V equals I times R. Right, so putting all this together, we've got this formula here. So there's two different forms, basically the same. So EMF is equal to the current multiplied by the circuit resistance plus the internal resistance. We could expand the brackets, so we have I times big R plus I times little r. Now this might look a little bit confusing if you haven't seen it before. It's basically the same as V equals I times R, because EMF, as we said before, is a voltage. Current multiplied by resistance, V equals I times R. It's probably more useful to think about this rearranged slightly. So we've said that I times big R is the terminal PD, or the circuit PD. This is the voltage we can actually get from the system. So we can make that the subject. And then if I take I times little r to the other side, so EMF minus the lost volts, this probably makes a bit more sense. What we're saying here is the voltage available in a circuit, given the symbol capital V, is equal to the maximum theoretical voltage, the EMF, take away the lost volts, which has been used up pushing the current through the power supply. In theory, this can always be a bit hard to grasp, but it's usually helped by doing a simple calculation. So let's work through this one. So I have a simple series circuit. I have an EMF of 6 with an internal resistance of 2 ohms. So very often we draw a circle around to combine those two, but not necessarily. So the internal resistance is 2, and I have 5 ohms and 5 ohms in series, so the total circuit resistance is 10. So the question says find the current. Okay, well we have our formula. E is equal to I times R plus R. So what we're doing here, to work out the total circuit resistance, it's just 5 plus 5 is 10, plus the internal resistance is 2. Now all we're doing here really is adding together 3 values of resistance in series. So even though this is an internal resistance, it's just in series with these other two. So 5 plus 5 plus 2 is 12. And then hopefully we can see this becomes a simple calculation. I is equal to the EMF 6 divided by 12, which is 0.5. So we found the current all the way around the circuit. As we've said previously, Kirchhoff's first law, the current is not used up. So the current is 0.5 here, 0.5 here, 0.5 here, all the way around. Right, so the lost volts we defined as I times little r. It's the voltage used up pushing the current through the internal resistance. The current we've established is 0.5 multiplied by the internal resistance of 2. 0.5 times 2 is 1 volt. To find the terminal PD, or the circuit PD, which we've said is the actual voltage we can get out of the system, there's 2 ways of doing this. Perhaps the most intuitive way is if I've said that 6 is the maximum theoretical and I've lost 1 volt, then 6 minus 1 is 5. That might be more intuitive. However, we can also calculate this with our expression here, I times big R. So the current multiplied by the circuit resistance, 0.5, Kirchhoff's first law, same all the way around, multiplied by the total resistance, which is 10, which is equal to 5. So what we're saying here is that the maximum theoretical voltage available is 6, but we're never going to get that because we always have a current flowing around the circuit and through the internal resistance. So we're always going to lose some of that 6 volts, in this case 1 volt, due to the internal resistance. So the actual voltage available is slightly lower. Now it's your turn to answer some questions. So pause the video and have a go at these 3 questions. Question 1, you need to know these definitions or descriptions of what is meant by internal resistance. So this is the resistance inside the supply because the current needs to flow through that resistance. What is meant by lost volts? So this is the voltage used up pushing the current through the internal resistance. And what is the EMF? In this context, this is the maximum theoretical voltage available. The actual voltage is the terminal or circuit PD. Question 2. So very similar to the one we did previously. So the way we do this is by using our new expression. E is equal to I brackets R plus R. So the total circuit resistance is 15 plus 15, which is 30, plus the internal resistance of 6, which is 36. So make I the subject, 12 over 36 is 0.33. We'll talk about rounding later on. The terminal PD, V is equal to I times R. So we can use our expression here, 0.33 multiplied by the total resistance of 30. So what I've done here, cheated a little bit to make the numbers a bit more friendly, because really we should round to 2 or 3 sig figs, which is what I've done. And then really I should use that value, 0.33, which would give me 9.99. But for ease of illustrating part D, I've rounded that up to 10. So this is something to consider about significant figures. The general rule, especially for practical questions and for core practicals, is that none of your answers should have more significant figures than we have in the original question or the measured raw data. However, you might be told in other subjects, for example in maths, that you should keep all the numbers on your calculator and only round up at the end. So there's different schools of thought. Just be aware of your significant figures, especially in the exam. Generally, if you write your answer to 2, 3 or 4 significant figures, then that will be acceptable from the examiner. The lost volts is I times little r, so it's our current, 0.33 multiplied by the internal resistance of 6. Again, I've rounded this up. This is actually 1.99, so I've made this 2. And then how can you check your answers? Well, hopefully we can see with our nice rounded numbers here that 10 plus 2 is equal to 12. So the lost volts plus the terminal PD add up to the total EMF. So if we wanted to explain why this was the case, we could say this is due to the rules of voltage in a series circuit, which is related to conservation of energy, as we saw earlier on in this series. Question 3. So always a good idea to draw a circuit diagram if this isn't provided. So we can work out the total circuit resistance. So 1 over 10 plus 1 over 40, invert your answer. So the total resistance, capital R, is equal to 8. And then in the same way, E is equal to I, R plus R. Stick the numbers in. In this case, we don't know little r. So expand the brackets. 0.5 times 8 is 4. 0.5 times little r. Rearrange to make R the subject and solve, we get 4 ohms. So this would be my recommendation for answering these questions. If you want to just treat this as a series circuit, once you've worked out the total parallel resistance, then it follows the same rules as V equals I times R. So some students decide not to even bother with this expression and just use their knowledge of current and voltage in a circuit. And that's absolutely fine. That does give you the right answer, but my recommendation would be to get familiar with this expression here. We really need to consider internal resistance in a practical application, partly because this is typically one of the core practicals for most exam boards. It's a very typical exam question, And it's, I think, a really important thing to consider. So if you're doing the practical, you'd use a variable resistor, either drawn like this or possibly like this. Very simple circuit. We'd have a fixed power supply, typically a battery, and we measure the voltage across that power supply, and we measure the current in series in the circuit. So we know our expression here, terminal PD is equal to the EMF take away the lost volts. I can rearrange this slightly to make IR to the other side. This is a bit more helpful. So V is equal to minus RI plus E. And then if I compare this to Y equals MX plus C, which is the equation of a straight line, what we typically do is we plot the terminal PD on the Y-axis, and we plot the current on the X-axis. If we do that, then we should get a linear relationship with a negative slope, and the gradient represents the internal resistance, as we can see here, and the y-intercept represents the EMF. So this knowledge of how to do the practical, what results you would get, what the gradient and the y-intercept represent are very, very typical exam questions, so certainly something to be aware of. Something else we might need to consider is, why do we get this negative correlation? So why is it that as the current increases in the circuit, then the available PD decreases? So this is a really important set of ideas. So first of all, what are we actually doing in the circuit? So we're changing the circuit resistance. So as we reduce that to make it smaller, then the current increases. You could say according to V equals I times R. So if the current increases, we know that I times little r, the lost volts, will also increase. Therefore, there is less voltage available in the circuit. In other words, the terminal PD, V, will decrease. And then you could make reference to V equals E minus IR. That could be a 4-mark question in the exam. As always, think about the terminology you use. Do make reference to a formula. Examiners like to see that because that is the, I suppose, the mathematical or the algebraic proof of what you're saying. Okay, a quick review of the key ideas. So just test yourself. What is meant by internal resistance, lost volts, and circuit or terminal PD? And then how would you find an experimental value of internal resistance of a battery? So pause the video and see if you can answer these questions. Okay, so make sure you've got your descriptions of these 3 terms correct, as we've explained previously. And as we just went through, how would you find a value of the internal resistance? So we need to describe the equipment and then get a range of values, plot the data, plot the terminal PD on the y-axis and the current on the x-axis, draw a straight line, and then if we work out the gradient, then the magnitude of the gradient is the internal resistance. We could also, for good measure, make reference to the y-intercept representing the EMF.